Okay, so for this question, you need to use the equilibrium data for ammonia water system given at the end of the tutorial sheet. So, well, actually in real life, you don't get the equilibrium data for the specific system or problem that you have, but rather you have to find out which one is suitable. For example, here, if you find in the Paris Chemical Engineers Handbook, you may find this table which look like this. So you want to decide on your own which of this table that is useful to you. So in this case, we can take the XA, i.e. the mole fraction of ammonia in the liquid phase, but rather than partial pressure and mole fraction in the vapor, Y, so we rather use Y instead of PA. Okay, and here our pressure is 1 atm, is the same for our system. And then the temperature that we're going to use is the 20 degrees Celsius, i.e. the 293 Kelvin, like what is provided in the question. So you can simplify this equilibrium data by tabulating the equilibrium line. So the x here is the same with what you have for the xa here, and the y star, i.e. y in equilibrium with the values x, are the one, oh I'm sorry, you need to use this one instead, I'm sorry. Okay, so you this one, okay, use this one. So just to simplify the data, so you can plot the numbers into a table, then you can plot the equilibrium line based on this table. So if you plot the equilibrium line, you get such curve. So it's not a straight line, so you don't have the usual y star equals to mx curve. Don't have this, so you need to use the equilibrium line to find out the x1 max, i.e. the x1 in equilibrium with y1, in order to find the minimum liquid flow rate. Okay, so if you recall our system, the our power, your y1 is 0 0.0 0.20, and your y2 equals to 0.0025, your x2 equals to 0, and your x1 we have calculated previously equal to, no, you don't know, you haven't calculated because you don't know the liquid flow rate, so you don't know the outlet liquid flow rate. So you need to find the minimum liquid flow rate first. So here, you know the coordinate for the top of the tower, 0 for the x-axis and 0.0025 for the y-axis. So here you can sort of know this is the point y2 and x2, but the thing is you don't know where is your x1 y1 point, because you don't know what is your x1. But in order to find the L min, you need to know what is the x1 max. So x1 max would be x1 in equilibrium with y1, and y1 is equal to 0.20. So you take the you plot from this graph 0.2, this is your y1, this is 0.2, and then you go all the way to the equilibrium line, and then yeah, this would be your x1 max. Okay, so this one is your x1 max, about 0.121. So you take note of this x1 max equal to 0.121 to find the L min. Okay, so we write down the operating line, v prime y1 1 minus y1 plus L prime x2 1 minus x2 equals to v prime y2 1 minus y2 plus L1 L prime x1 1 minus x1. So at L prime equals to L prime minimum, and x1 will be equal to x1 maximum. So you replace everything with that. So v 1 minus y1 plus L prime min times x2 1 minus x2 equals to v prime y2 1 minus y2 plus L prime min, and then here x1 max over 1 minus x1 max, and then you put put in the known values, b prime, y1, x2, b prime, y2 you also know, x1 max we already found out, and then now you just need to find what is the L min. So you key in the numbers and try to solve for L min. So you can simplify the equation also. So L min times x2 1 minus x2 minus x1 max over 1 minus x1 max equals to v prime y2 1 minus y2 minus y1 1 minus y1. Then L min prime 0 1 minus 0 minus 0.1 to 1 over 1 minus 0.1 to 1 equals to v prime 0.80. Y2 0 to 5 1 minus 0.00 to 5 minus 0.2 over 1 minus 0.2. Then solve for L min prime. Then you get L min prime equals to 1.438 mole of water. In this case, the liquid flow rate is water per mole of entering gas. Okay, yeah, so that is your L min. So the next part of the question is part B. So we're in part B, what would be the NOG, number of overall gas transfer unit, to be used if your actual liquid flow rate L prime is 40% greater than the minimum liquid flow rate. So in this case, your L prime is 1.4 times the L prime min. So you have calculated the L prime min, so you can just key in the numbers. 1.4 times 1.438, so this would be equal to 2.013 mole for the actual liquid flow rate. So here we need to find the operating line coordinates. So here recall your columns. So you have your y1 equals to 0.2 and your y2 equals to 0.0025. Your x2 is 0, it's pure water, and now you can find out what is your new x1, given that now your L prime is 2.013 mole. So we can use the modified operating line equation. So L prime times x1, 1 minus x1, then x2, 1 minus x2 equals to v prime y1 1 minus y1 minus y2 over 1 minus y2. Then put in the numbers. So L prime is now 2.013. X1 is what you want to find, and x2 is 0, so everything there will be 0. And v prime is 0.80, and y1 and y2. Then get x1, and x1 is equal to 0.0896. But since this is not a dilute solution, and we've seen that also the equilibrium curve is not a straight line, we would expect that the operating line would also not be a straight line. So we need to find some intermediate points between the top between the top and the bottom of the tower. So we need to find intermediate points between 0.0896 and 0.20 and 0.0 and 0.0025, i.e. this is at the bottom and this is at the top of the tower. So we need to find somewhere there. So yeah, up to you which one you want to use. Let's use this equation, modified equilibrium line equation. So let's say if you set x equal to 0. Okay, sorry, let me do that again. Let me start over. So we can modify our equilibrium line equation from here. So we have 2.013 times x minus over 1 minus x, and then because if minus 0 x2, then it will be 0, meaning we now take the control volume here. Okay, so here we would have y, and here we would have x. So then our control volume is there, so we can modify the operating line equation. Then 0.8 times y minus 1 minus y minus this part here. Then that one is actually 0.002506. Then, so if we put any value of x, let's say we put x equals to let's say x equals to 0.008, put in this equation, then we get y equals to 0.0223. Then repeat the same thing to get another intermediate point. So let's say x equal to, so if you put another x value, for example, x equals to 0.025, then you get y equal to 0.0628. And to ascertain further what is the shape of your operating line, then you can also add another x value. Let's say x equal to 0.05, then you will get y equals to 0.1189. So you now have 5 coordinates. Okay, this is 5. Okay, so you have now 5 coordinates, which are this one 0 and 0025. This one x1 is 0.0896 and 0.2. Then this is another point, this is another point, and then this is another point. So you have 5 points to plot the equilibrium operating line. Okay, so here you can plot the operating line and equilibrium line. So if you see previously, the blue line is the equilibrium line as given in the table, and then this table here shows your operating line coordinates. You have 5 points, so the x values and the y values, so you just plot, and the orange line here is your operating line. So now your job is to calculate the energy. So whenever you want to calculate energy using the overall gas phase, then you need to find out what is this y star. Okay, so you find out what is the y star. So y star here is the y in equilibrium with the x. So when x is 0, then y star will be equal to 0. Then when x is 0.008, you read from the graph where is 0.008. So here 0.008. Then you read, then maybe about 0.01. So yeah, proceed as next part is 0.025. Then you get about 0.032, and then 0.1189. Oh no, 0.05 here. Okay, you get about 0.068 here. Okay, and then lastly 0.2. Oh no, not y, x. 0.0896 or close to 0.09. Then you read the equilibrium curve. Then you get y star is about 0.133. So these are the values that you're going to use to calculate your energy. Okay, so previously you've seen this, that equals to HOG times energy, but in this question you are only asked to find out the energy. So Z equals to HOG, this is HOG and this is energy, so we can take out the equation for energy only. So here you have the log mean 1 minus y star, then that is equal to this part here is equal to this part. So what you have to do is you need to tabulate the data. So from here, you have your x, you have your y. So these are your operating line, and then I've shown you how to read the y star from the equilibrium line just now. And then since in your energy, you need to have the term y minus y star. So you you have another column y minus y star, so that is actually this y here minus y star, then you get this column, these numbers for each row. And then another thing is you also need to get the log mean y minus y star m. So you need to get this. I mean, the idea is here, to calculate the energy, you need to integrate from y2 to y1. Okay, you see this equation here, right? So i.e. now with respect to y. So you need two columns to do the integration. This column here is your y, and then the y-axis of this graph is the whole thing here. So that's why you need this thing. So you calculate. Now you have y star, and then you have y minus y star m for each y point. So you just key in the formula, then you can plot the graph where the x-axis and y-axis. So the y-axis, the horizontal axis is the y value, this one, and the vertical axis is this whole thing here. Okay, so if you can plot this graph, I will show you in the next slide. So you plot the graph. This is the vertical axis is your y. So y goes from 0.0025 to all the way to 0.2, and then the corresponding value of the integral, I mean the y minus y star and so on and so on, right? So you plot this graph, and then the goal is to calculate energy. So energy is the integration from y2 to y1, this whole thing here with respect to y. So in other words, is the area under the graph. So then you just have to calculate what would be the area under the graph. Up to you. This one you've done so many times before, and then I will just give you the final answer. Energy, you should get about, I don't know, 8 point something. Okay, so if in actual case you have to find the height of the column, z equals to HOG times energy. But in this case, the question only asks us to find the energy, since maybe we don't have enough information to calculate the HOG. But if you were given enough information, or if you have to find out what is the actual height of the column, then you need to find out what is HOG. Then you know what you need to do to get the HOG. It's the V over KY A times S. So you need the KYA value, D is the gas flow rate value, and S would be the area, cross-sectional area of the tower. And to get the good number of cross-sectional area, you need to also consider the vapor flow rate to liquid flow rate ratio to avoid flooding, weeping, and everything. Flooding, weeping, and what is another foaming? Yeah, foaming. I mean, the principle of designing an absorption tower is same with the principle of designing a distillation column. Whether it's packed or tray column, you need to have a good ratio of vapor to liquid flow rates. Okay, so that's all. Thank you.